All right. Before we start, any questions? Concern? All right.
Yes, sir.
If not, then let's start with another example. So let's pick up a problem from the exercise. Okay. So problem say 14.3. Problem. So B is flying upward along a curve, which is intersection of this surface. Okay, so power 4 with the plane x equals 1. So intersection of two surfaces, okay, is a curve. So that's the curve of the what you call the path of that bee flying. Okay, so let's see. So generically, we always draw the plane. This is the general surface. Okay, and then you uh, with the x equals 1. This is y, this is z. Okay, so this x equals 1. Then you have a, say, a kind of wall. This is the intersections. There. Okay. So this is the intersections. This is the path of the B. Right? And at some point, and when at this point, it's went off the tangent line. Okay. So the question is, where did the B hit the XZ plane? XZ plane is this one here. So for example, so B is flying in this directions. And B is flying these directions. Okay, and suddenly here it's went off the curve along the tangent line. So this tangent at this point. So it went off and hit this plane here. So the question is, what's the coordinate of this plane here? So this plane here has a the y is 0, so this is x, say tilde, y equals 0, and z tilde. So what is this at this point? Okay, so that's the questions. Okay. All right. So the slope of this um, the slope is nothing but the f of, say, f here is defined x to the fourth plus x y cube plus 12. That's our f. So here, as at the plane x equals 1, so we fix x equals 1. Fix x, vary y. So that means we vary y. This is the equation. Okay, so compute the slope is this, right? Have computed at this point here. 1, -2, 5. Uh, my sharing started stop a little bit. Okay, can you see the screen already?
Yes, sir.
All right.
Yes, sir.
Hello.
Yes, sir.
Yes, sir.
Okay, so just pick up your microphone, unmute, and just mention it. When I'm sharing, I barely can hear the whole screen. Sometimes your reaction, I cannot see your reactions here unless I unshare first. All right, so here we go. So this is computed at point 1, comma. Right. So this is the we need to compute. Okay. All right. So let's compute this one. So df dy is that's easy. So the only y symbol there is xy cubed. So you think x as a constant. It's an x constant. So you have 3xy squared. So that's it. All right. And compute it at 1, -2. Here is 3, let's see, 3, 1, 4. So that's 12. Okay. So this directional factor here, now we need the equation for the tangent line. Right. Okay. So the tangent line passes through the point 1, -2, 5. Right? Is given with directional factor is, let's see, this is slope 12. So the directional factor is it doesn't change the x because that's along along this on this let's see, this wall, the wall x equals 1, right? So the directional vector is 0, x, and then the y dx is 12. And what about the z? Z here is, let's see, how to compute the directional vector. I forgot. Uh, X, oh, it's going that direction, it's going to the left. Slope 12 means u rises by 12 if you move by 1. Okay, so the directional vector should be, if you move x by 1, then the y move by 12. Okay, and all right, so this is the directional vector. See, what's wrong with this one? I slightly forget this. Hmm. This is C. This is Y. The directional vector is something that looks like one. X doesn't move. 0. Okay, so the directional vector means, sorry, this is wrong. All right. It doesn't move along z, so this is going to be along x, so this is 0. And when you move y 1 to the left or to the right, and you rise up by 12, this move. Okay, so then the directional vector is 0, 1, 12. So equation for the line is just 1, -2, 5 as vectors plus t plus this directional vector. Okay, so you get these equations. So this is 1, right? -2 plus t. Okay, so t minus 2, and 5 plus 12t there. So in parametric form, Well, t is any real number. So in parametric form. Remember that if you have a line passes the point, say ABC, with directional vector alpha, beta, gamma is A plus, sorry, ABC plus T alpha, beta, gamma. Okay, so that's equation for the line in free space. Okay, and now the question is when it hit this one here. Okay, question is what makes this going to be 0? Okay, so the y is 0. I've at XZ plane when y equals 0. Y equals 0 means this one here. So t minus 2 equals 0. So you get when t equals 2. Okay. So when t equals 2, you see this is position. The position factor at a equals 2 is, let's see, this is 1, this is 0, this is 29. Okay, so now the conclusion is that the P lands at this point here, 0 on XZ plane. Okay. Questions? Right. If not, then let's continue this. All right, let's go on to our next sections. This is about limit and continuity. So the question about limit is rather different from limits in one variables. Okay. So let's skip this one first. Let's see the reason why. Okay, the main difference is that if you have one variable and you have this limit, okay, so that means you have a point A and this limit, meaning that if you have x on the right approaching A, so you only have two approaches basically. Left, all right, two directions or two approach or direction. Okay, on the left, right here. So coming closing gets closer to A from the left or gets closer to A from the right. Okay, so now that is the reason why limit exists if, see, both directions from the right and this approach, A from the left, give you the same thing, right? So that's what you call the limit. Okay, so going from the left or coming from the right give you the same limit, right? Now, if you have in a plane on the xy plane, so meaning that you have two variables, right? So as you have two variables, if you have two variables, this is the case. So this point, say x0, this is point A, this is B. The question is, how are you going to approach this point here? Uh, how to approach the point this direction on xy plane? Well, there are so many directions. Okay, so left and right are just two directions, going from up, down, right? Any directions. And even the more extreme one going there. So this is the problem. There are infinitely many ways to approach point A. So that's the basic the problem. So how do we know if they all give you the same limit? They give the same limit. So this is the basic problem for this example. Okay, let's see this limit here. Say is this is whenever x not equal to, of course, when this is not. Okay. So the question is when whenever we approach, including 0, 0 here, do we get anything? All right, so let's see here. So we are trying to approach this point, 0, 0. All right, so coming this direction. Coming this direction, meaning y equals 0 and x equals is going to there from positive. Okay. Coming there, you see that the this is 1. Okay. Y equals 0, so you get this one. Okay, so equal. So this approach. Let's see. I think yeah. Right. And now when you approach from this direction, that directions, this is x equals 0, y going to 0. This is 2. So then x equals 0. Not exactly the thing that I want. All right. Let's go back to this one here. What's wrong? So postpone this a little bit here. This shows you a two approach of this one. We should proceed with the another approach. Okay, so we'll see this one. The question is another approach. We'll go back to this question later. Right? And second would be here. Okay, so this is for x, y not equal to 0. So the question is, does this limit make sense? Okay, so we try to approach this one here. All right, so the same fashion as before. So coming this direction. Coming this direction means y equals 0, x going to. Okay, so this approach gives you so in this case, you see that y equals 0. Okay, so what's the remain is x going to 0. Okay, so just plug in y equals 0. Y equals 0, then just x squared divided by x squared. So this limit was 1, right? But as we coming this direction, so this direction, in this direction, y x equals 0, but y going to 0. So the second approach gives you, let's see, x equals 0 to 0, y. That's this just limit of one variable. X equals 0 to this negative y over y squared. This negative 1. So you end up with a different number. Okay. In fact, if you approach using this one here, this y equals kx. Okay, so this y equal kx. So just x kx. Okay, and so this is just one variable. So pushing x going to 0. Okay, so what you have here, so this x minus kx squared. Then you have x squared plus here you can do some simplifications because you can factor x square out. So 1 minus k squared, 1 plus k squared. So this cancel. So at the limit, you only have okay. So of course, this approach is this all different thing with a different k. So here, different limit. Okay. So what tells you that any direction here give you different thing. Okay. So in this case, you cannot say anything, say approaching 0, because it depends on how you approach. So this one here, this only there depends on how we approach 0. So this is one complicated thing about a limit of 2 or more variables because you have infinitely many directions. Okay. So then it is easy now to state a criteria here that of functions with 2 or more variables exists if it is of the approach. Fraction of the approach. Okay, so meaning that it will give you all the same approach. Okay. So let's compute how do we know that it's independent. All right, so let's just do some easy case. limit exists here. Okay. Don't prove this, but we just use this one here. Okay. If a f is polynomial, then the limit is just you just plug in number as usual. Okay. If f is a polynomial over polynomials, so rational functions in two variables, then the limit is just again you plug in a number, provided that the denominator is not zero. Okay, and if the limit of the numerator is L, the limit of the denominator is zero, then this limit does not exist. Okay. So we just put this one and we'll use this. Okay, this is what I call easy case when limit exists. All right, so let's do some computations. Big example. Just mention this one here. This is a example. Before we do the example, just look at this example here. This is x squared y with cy. This is polynomial. Okay. So the limit is obtained by just plug in numbers here. Plug in numbers 1, 2, 1 for x, 2 for y. You can. Okay. And the second one, see, if you plug in 0, 0, x equals y 0, then the denominators is 0, but the numerator is non-zero. It's going to 1 limit. So this doesn't exist. Okay. All right. You see, this is the one that they compute before. So if we plot this in Maple or Mathematica, whatever you like, your favorite apps, okay, the function looks like this. So somehow it's not defined at 0, 0. And when you have a 0, 0, the thing here is that you get a indeterminate form, 0 over 0. Okay. However, now this you don't have a L'Hopital rule for two variables limit. So there's nothing to simplify this one. Okay. Okay, so this approach, when y equals 0, that means approaching this direction or this direction. Here, this limit is 1. But when you approach from The second one is from above or from below. So y equals, sorry, x equals 0 along x-axis. Sorry, this should be this one. It's -1. So we say this doesn't have limit. Do some more example when limit exists. Here, for example, let's just do this directly. Okay, can you see the page of the problem set?
Yes,
Yes.
sir.
Yes, sir.
Okay. Something wrong. All right. Turns out that my speaker is somehow is connected to the external speaker, not to my earphone, my earbuds. All right. So, okay. Good. All right. Please help me. Can you someone talk to me?
Test,
Uh,
test.
check my whether my speaker phone is okay.
Hello, sir. I'm testing. I'm testing.
Huh. Still cannot hear Aska. What's wrong with this one? Okay. All right. This one first. Okay. Let's do the what I'm doing here. Okay. Let me share this one. Okay. Let's do some couple of problems from the exercise. For example, this one here. Computing this limit. This is a polynomial. So this is the case when you just plugged in a number. Okay, so when you plugged in the number, you get 3, 1 squared times 3 minus x is 1, 3 cube times 3 cube. All right. So you get, let's see, this is 9 minus 27. So this minus 18. So then that's easy. Same thing with number 2, just plugged in the numbers. Okay. And problem 3 is not polynomial because you have cosine and sine. But I won't prove this, but just similar. The thing is, when you plug in numbers, the idea is, yes, when you can plug in numbers, yes, just plug in, and let's give you the limit. Okay. As long as you can plug in a number and give you a number, and that's the limit. Okay. So the problem now is that when even number 6 looks ugly first, but then that's become easy because xy is 0, but cosine x is 1. Same thing here is xy is 0, approaches 0. This approaches 0, but this approaches 1. This approaches 1. So this -1. So the thing is, you get the limit is -1. The thing you can just plug the number. Now this is rather different. Okay. Here, number 7. Sine x squared plus y squared over x squared plus y squared here. Okay. So let's see. Just think this is a, let's do this one. Okay. So this limit or whatever there is polynomial. Just plug in numbers. Let's see, this is 1, 2 cube, 1 square. So this is 8 plus 4, 12. So this is the gives you a value. Then it is likely the limit. Okay. So the question is this one here. So the question is problems when we encounter indeterminate form. What do you call this? Indeterminate, yes. Okay. Then you need some simplifications. factorizations. One thing is factorizations. Okay, so for example, here, limit. Now this is the one that we did earlier. Okay, this is 0/0. Okay, but we can do some factorizations because here you have x squared plus y squared. Plus y squared, right? And you can cancel this two, right? And leaving you with this one, this polynomial. Okay, become green, sorry. And here's the case, it's polynomial. Again, you can plug in numbers and give you 0. Let's leave it. Okay. All right, so this is what I mean by doing simplification, doing factorization. This is the most likely situations. Okay, but now I should warn you, because this is a common mistake. No version of L'Hopital rule for limit two or more variables. So that's a problem. Okay. So you cannot do L'Hopital in this case. Okay, so this is the important thing. So you left with the not having discomfort of having L'Hopital. Okay, let's do this one here. What about this one here? I'll say this one. Okay, so it looks like if say x tilde is just this limit has the form of this one. So limit sine x over x, something like this, which has 1. We know this limit. So the thing is, how do we justify this one? Okay. So actually this is true, but we need some more tricks. Later on we use these tricks. Okay. So let's see, just show you this one. Here. This a here. Okay, so sine x squared plus y squared over x 3x squared plus 3y squared. So you can take the 3 out and then get this form. So in this case, r squared equals x squared plus y squared. So in the end, you have something like this. Okay, so just 1/3. Now, because this is one variable, okay, you can use L'Hopital rule. So L'Hopital rule is used here. Okay, but no way you can use L'Hopital at this stage here. Okay, so L'Hopital rule is used for one variable when we reduce the variables to one. Okay, that's one. Well, I'll explain this later about this strange substitutions. This is polar coordinate, something that we skip. Okay, we'll stop here and then take a break and continue with this. Continue with these sessions. All right, so I'll stop here and stop record and